Welcome back. We were doing a certain quick calculation to see if a VSAT directly communicates with another VSAT via satellite in one single hop, what should be the power requirement at the VSAT. We have taken both VSAT size same, efficiency same, uplink and downlink frequency. We have taken some numbers and we started the calculation and we were in between the calculation. So, if you recollect, let us go back. We were calculating the receive antenna gain, got 39.8 dB, transmit antenna gain is 41 dB, both for VSAT. For different frequency it is different, and we tried to calculate the G by T. For that we have seen the receive noise temperature based on the figures which are given. We got T as 20 dBk and G by T as 19.8 dBk. Now let us calculate the losses. The downlink loss is 4 pi this R, that is the range, f by c, and then this is whole square, which this is in kilometer. It was given 40,000 kilometer. You have to convert into meter because c you will take in meter, and this f is in hertz. So with all these things, with log you will get a number as 206 dB approximately, and similarly the uplink you will find the range of the using the same expression, only the f here it is receive and f here is transmit. So the numbers will be varying. Transmit frequency is higher, you will find 207.4 dB, 207.4 dB. We will keep these numbers, it will be useful, and let us try to find out now C by N naught required. This can be found out from what is EB by N naught required and in dB and the bit rate, which is EB by N naught was given 5 and bit rate was given 8 megabits per second. So it is 8 into 10 to the power 6, which comes out to be, these will be 1 megabit is 60 dB and 8 megabit is 9 dB more. So 69 dB and 5 dB together it will give 74 dB hertz. Now remember, C by N naught required in the totality, the whole link. So therefore I can call it, it is same as C by N naught total. Now if you remember, we said at the beginning C by N naught of the uplink and C by N naught of the downlink are same because the same sizing is used, and if they are same, then C by N naught total will be 3 dB lower than any one of them, C by N naught down or C by N naught up, or I can say C by N naught down is C by N naught total plus 3 dB, and C by N naught total we got. So therefore C by N naught down is 74 plus 3 is 77 dB hertz. You have understood the way we calculate. So we come to know now what is the C by N naught down. So one side link is known, and since the other parameters of that link is known, we can find out what is the EIRP from the satellite. So now in the downlink, C by N naught down is EIRP from the satellite plus G by T of the VSAT minus loss, path loss in the downlink, minus miscellaneous loss, minus k, that is Boltzmann constant. So therefore EIRP of the satellite is C by N naught down minus G by T of VSAT plus loss in the path loss in the down plus loss the miscellaneous plus k. Now this value k, if you remember, it is minus 228.6 dB per k per hertz. So, if you put the numbers 77 minus that is 19.8 if I recollect correctly, this was 206, this was 2, and then this is minus value. So, minus 228.6, that gives a number as 36.6 dBW. Now, we know the satellite EIRP. This satellite EIRP, this side is known, that is the downlink. EIRP satellite is known. Now, as we have said, there is this whole satellite including the antenna has a gain G is given, how much was given, 166 if I recollect, 166 dB. Transponder gain is 166 dB, satellite gain is 166 dB. So, that block, this particular block is 166. So, EIRP minus the gain is the input power which is the satellite, plus the uplink losses. If I add the uplink losses, then we get the EIRP here, that is the EIRP of VSAT. So, therefore, we can write it this way: EIRP of VSAT is equal to EIRP of satellite, and then I reduce the gain, that is the satellite gain, and then I add the losses, uplink and miscellaneous losses. So, that comes out to be 36.6 minus 166 plus 207, uplink was larger, 207.4 plus 2, that comes out to be 80 dBW. 80 dBW we got, EIRP of the VSAT. Now, if we try to calculate the VSAT transmitted power amplifier out, which will be the whatever is the EIRP of VSAT minus the gain of the VSAT transmit, and then plus some losses, that is feeder loss. This is 80, and if I recollect the antenna gain, which was calculated as 41 dB, transmit antenna gain, it was calculated as 41 dB. So, we put 41 here, and feeder loss was 1 dB. So, this comes out to be T plus 1 E2 and 40 dBW. Now, what is the meaning of 40 dBW converting to watt? So, this is approximately 10 to the power 4 watts. Means 10 kilowatt, 10 kilowatt of RF power output. So, the DC power requirement is, depending on the RF power amplifier efficiency, is much larger than 10 kilowatt. It is not possible to provide such high RF power at VSAT location. Remember, we were talking about the VSAT location which are at bank ATMs, etc. So, normally very high wattage is not used, as a smaller capacity. This may be possible in a large station. So, if you want to communicate of 1 meter to 1 meter VSAT with 8 megabits per second with certain gain of the satellite antenna, satellite system, you get a absurd type of DC, I mean RF power requirement, corresponding DC power requirement. So, what can be done? I can do one thing, I can increase the receive antenna size. So, change the or the transmit antenna size, any one of them. So, change the transmit antenna size to 9 meter, instead of 1 meter I change it to 9 meter with the efficiency. Obviously, efficiencies are better, we have discussed earlier. So, GT is efficiency into pi d f by c whole square, which will come out to be roughly of the order of 61 dB. Now, then the HPA out, that is our PT, is 80 plus 1 minus 61, which comes out to be 20 dBW, which is roughly about 100 watt, which is tolerable, So, all VSAT has large station, we call it hub station at other end. Now, you will realize what is the word hub. There is a VSAT which is communicating with a station which is of course via satellite, which is large station. There is another VSAT which is communicating with a large station. So, all VSATs are communicating with the large station. So, in a total network of VSATs, we have one central station which is called, obviously you can call hub, and it is a star type of configuration. One big advantage is star type configuration is the routing from VSAT to VSAT can be easily done at one place. One of the big basic disadvantage, that is you are communicating from VSAT to hub to another VSAT. So, if there is a real time communication from this VSAT to this VSAT, you will need 2 hops, and each hop is 250 millisecond. So, therefore, half a second will go to reach there. So, real time communication is not suited in this type, but non real time. That is why it is in the ATM, that is the bank transaction or commercial transaction where data communication is taking place. Then therefore, people try to do real time communication with a larger type of antenna in the VSAT, and it is possible that a VSAT to VSAT in one hop, you can use a VSAT antenna of the order of 2.5 meter or so. The corporate offices, when they have this VSAT network by their own, they use this type of thing where it is much more tolerable. You have a single hop communication. In this process, I will try to show you how to calculate the number of carriers that can be supported by a satellite. Let us take those number, that is hub with 9 meter antenna and 8 Mbps rate. The satellite EIRP we have already calculated as 36.6 dBW. Now, transponder EIRP is of the order of, in the linear region of linear operating point, in the linear region of operation is of the order of 42 dBW. So, the number of carriers is 42 minus 36.6 is 5.4 dB, which corresponds to roughly about 3 carriers. So, but then if you if a VSAT is communicating to a hub, the hub antenna is 9 meter. So, its G by T of hub is quite large. It will be of the order of 20 dB more in this particular case than VSAT G by T, what we earlier calculated as almost near 20 dB per K or 19 point some dB per K, roughly this is approximately 20 dB. So, since this is 20 dB more, so therefore, from the satellite the EIRP per carrier VSAT carrier will be could be 20 dB less to maintain that. And what is the 20 dB? 20 dB is equal to 100. So, there are 100 times more carrier, 100 times more carriers that can be used for VSAT to hub. So, therefore, people normally use a separate transponder for hub carriers and separate transponder for VSAT carriers. These things we can go on calculating for using different numbers of hub and different numbers of VSAT. So, there are different types of VSATs. That is receive only, that is for broadcast TV reception called DTH. Its antenna is very small and the of the less than 1 meter, and only receive chain is there. Then transmit receive via hub. This is a star configuration and non real time application, like we have seen in VSAT for bank ATM, etc. Then another thing is there, that is transmit receive not via hub but direct from VSAT to VSAT, that is in mesh configuration. And this is real time because one single hop it is going. This is for corporate network where real time communication is required, and there could be transmit only, that is to hub, and it is a star configuration. Examples are automatic weather station, we explained. Also it could be the broadcast hub, that TV transmission is done by the hub station for broadcasting. So, that is only one uplink. So, that is transmit only. It could be very large or it could be very small depending on the requirement of the type of VSATs. These could be different categories of VSATs. Now, let us after seeing this quick calculation and why in a network a small station needs always a large station at the other end, let us see some more important issues. That is, the earth terminal, earth station are having some important parameter, that is let us go back to our transmission equation. C by n is Pt Gt. I continue to repeat this so that you get familiarized with this one. 4 pi r by lambda whole square into 1 by k. Now, you just see I put C by n. So, n naught is not there. So, bandwidth will come this side, another way of presenting, and G r by T. This T is system noise temperature of this is in ratio. It is not in dB. In dB it will be just 10 log and plus of that. But in this one important thing is this particular thing, which is G by T, which is called receiver figure of merit. It talks about the receiver antenna gain and it says that receiver noise temperature. So, the performance of the receiver is seen from here, and these two units, that is Pt and Gt, talk about the transmit system of the station. Now, to know the performance of the station, we must know how do we measure this thing. So, let us go into a technique, a topic which is called G by T that is, what is G by T? We repeat that G by T is 10 log of the receive antenna gain by receive so once we made it 10 log, so it is dB per k. Now, we will continue to discuss on this particular subject, that is the measurement. Now, G by T can be done in various ways. One is direct method, one is indirect method, sorry, and another is called comparison method. Normally, the problem is this antenna is a aperture which is communicating to the free space. Now, if you try to do a measurement inside the laboratory, just like as we measure the gain of an amplifier or noise figure or noise temperature of some subsystems, it can be measured with giving certain input to the system and seeing its performance with that input through a output, monitoring the output in terms of a power measurement or any other type of measurement. But giving a input to the antenna, you can see there is a free space, and if the antenna is large enough, which is 9 meter or 10 meter or 14 meter, it is a real problem. So, therefore, these measurements methods and techniques you have to understand carefully, otherwise it has to be only remain as a calculation. Now, for very large station, antenna, there we use this direct method of G by T measurement. That technique is similar to technique is similar to, since the temperature is there, if you remember the noise temperature measurement, we have told you that there is a method which is called Y factor method. So, it is similar to Y factor method. Y factor is measuring the noise temperature and the device temperature of two different loads connected at the input to the device under test. So, two different noise sources, and then ratio of these two measurements gives us a factor called Y, and you can calculate based on the Y and the measured noise power, you can calculate and find out the noise temperature. So, similar techniques are used here, and since the aperture is very large, they are putting a noise source in front of the aperture and calibrated noise source, that too is a difficult scenario. So, we will try to discuss and find out how it is done in the next class. Thank you for the time being.